Section 1, the biggest question in physics. Have you ever looked up at the night sky and wondered, what is it all made of? This might sound like a question for a philosopher, but it's actually at the heart of modern physics. Imagine an equation that could explain everything in the universe, from the smallest particles to the largest galaxies. This is the dream, the holy grail that physicists call the God equation. But is it even possible? To answer that, we need to understand the forces that govern the universe. Our goal is to find a single framework that can explain all these forces as different aspects of one fundamental force. Our journey begins with a tale of two incredibly successful but fundamentally different theories. One theory is general relativity, Albert Einstein's masterpiece describing the universe on the grandest scales. But then we zoom in to the realm of the incredibly small, the quantum world, where the rules of general relativity break down. This is where quantum mechanics comes in, governing the interactions of particles at the subatomic level. It's bizarre, counterintuitive, but one of the most successful theories in all of science. We have two pillars of modern physics, general relativity and quantum mechanics, each dominating its own realm, but what happens when we try to merge them? This is where our current understanding falters. The equations of general relativity and quantum mechanics simply don't align. The quest for the God equation aims to reconcile these two theories. This journey has led us down some strange and fascinating paths, from string theory to the possibility of hidden dimensions. Our story begins in the 17th century with Sir Isaac Newton. Before Newton, the heavens were seen as a mysterious realm, governed by different laws than those that ruled the Earth. With his law of universal gravitation, Newton showed that the same force that makes an apple fall to the ground also holds the moon in its orbit around the Earth. Newton's universe was a clockwork universe, a predictable and deterministic system. His work laid the foundation for classical physics and inspired generations of scientists. Fast forward to the 19th century, where we meet James Clerk Maxwell. At the time, electricity and magnetism were seen as separate phenomena, but Maxwell saw a deeper connection. Through his equations, he showed that electricity and magnetism were two aspects of a single fundamental force: electromagnetism. His equations predicted the existence of electromagnetic waves which traveled at the speed of light. Maxwell's work was a triumph of unification, a major step towards our goal of finding a single theory that explains all the forces of nature. By the end of the 19th century, classical physics seemed to be on the verge of achieving its ultimate goal, but beneath the surface, cracks were beginning to appear. Experiments started to reveal phenomena that couldn't be explained by classical physics. The double-slit experiment showed that light could behave as both a wave and a particle. These were fundamental challenges that shook the foundations of classical physics. As the 19th century drew to a close, physics found itself at a crossroads. Enter Albert Einstein, who proposed that space and time were intertwined in a flexible, four-dimensional fabric called space-time. In 1905, Einstein published his theory of special relativity, which shattered the Newtonian view of the universe. He showed that time was relative to the observer's motion and introduced the famous equation E equals mc squared. This equation implied that mass could be converted into energy and vice versa, a concept that would have profound implications for nuclear physics. Einstein's special relativity was a revolution, but it was only the beginning. In 1915, he developed his masterpiece, the theory of general relativity. In general relativity, gravity was a manifestation of the curvature of space-time itself. Massive objects like stars and planets warp the fabric of space-time around them, dictating how other objects move. general relativity, made several startling predictions which were soon confirmed by observations. Einstein's theories of relativity had profound implications for our understanding of the universe's most extreme environments. One of the most bizarre predictions of general relativity was time dilation in strong gravitational fields. General relativity also predicted the existence of black holes, objects so massive and dense that nothing can escape their gravitational pull. These cosmic monsters form when massive stars collapse at the end of their lives. Black holes represent a breakdown of our current understanding of physics, as the laws of general relativity break down at the singularity. Einstein's theories of relativity revolutionized our understanding of gravity, space, and time, but they also raised profound questions. One of the biggest challenges is reconciling general relativity with quantum mechanics. General relativity describes the universe on the grandest scales, while quantum mechanics governs the interactions of particles at the subatomic level. These two theories seem fundamentally incompatible. Despite these challenges, physicists remain optimistic that a unified theory is within reach. Just as Einstein was reshaping our view of the cosmos, a revolution was brewing in the world of the very small. Classical physics failed miserably when applied to the atom. These anomalies gave birth to quantum mechanics, a radical new theory that emerged in the early 20th century. In the quantum world, certainty gave way to probability, and the very act of observation seemed to influence the observed. One of the key figures in this quantum revolution was Max Planck, who proposed that energy came in discrete packets, or quanta. One of the most mind-boggling aspects of quantum mechanics is the concept of wave-particle duality. In the quantum realm, particles like electrons and photons can behave as both waves and particles. This strange behavior is linked to Heisenberg's uncertainty principle. The more precisely we know a particle's position, the less precisely we can know its momentum, and vice versa. It's as if nature itself is inherently fuzzy at the smallest scales. As physicists delved deeper into the quantum world, they realized that even the concept of particles as tiny, point-like objects was not adequate. This led to the development of quantum field theory in the mid-20th century. In quantum field theory, the universe is populated by underlying fields that permeate all of space-time. Particles are merely ripples or excitations in these fields. Quantum field theory forms the foundation of the standard model of particle physics, which describes the fundamental forces of nature except gravity. Einstein's general relativity describes gravity as the curvature of space-time. Quantum mechanics describes a world of discrete quanta, governed by probability. These two views of reality seem fundamentally at odds. Attempts to combine them into a unified theory face formidable challenges. The mathematics becomes incredibly complex, leading to nonsensical results. This incompatibility is acute in extreme environments like black holes or the Big Bang. Our current theories break down, suggesting a deeper understanding is needed. Reconciling gravity and quantum mechanics is the greatest challenge in modern physics. This quest has spurred radical ideas like string theory and loop quantum gravity. The search for a theory of quantum gravity could reshape our understanding of reality. The search for a theory of everything, a framework that could reconcile the seemingly incompatible worlds of general relativity and quantum mechanics, has led physicists down some strange and wondrous paths. One of the most promising and mind-boggling of these paths is string theory. String theory, at its heart, is a radical departure from the traditional view of particles as point-like objects. Instead, it proposes that the fundamental building blocks of the universe are tiny, vibrating strings, far smaller than anything we can currently observe. Imagine these strings as incredibly thin rubber bands, each a billionth of a billionth of a billionth of a centimeter in length. Just as a violin string can produce different notes depending on how it vibrates, these fundamental strings can vibrate at different frequencies, and each frequency corresponds to a different particle. So, an electron might be a string vibrating one way, a quark another way, and a photon yet another way. This elegant idea has a profound implication. It could potentially unify all the forces of nature, including gravity, into a single framework. Just as the different notes of a violin are all produced by the same vibrating strings, the different forces of nature could be different manifestations of the same fundamental strings vibrating in different modes. But one of the most intriguing and controversial aspects of string theory is its requirement for extra dimensions of space beyond the three spatial dimensions: length, width, height, and one time dimension that we experience in our everyday lives. String theory, in its most consistent forms, requires 10 or even 11 dimensions to work mathematically. But if these extra dimensions exist, why don't we see them? String theorists propose that these extra dimensions are curled up or compactified at incredibly small scales, far too small to be detected by our current instruments. Imagine a garden hose viewed from a distance. It might look like a one-dimensional line, but up close you can see that it has a second curled-up dimension, its circumference. Similarly, the extra dimensions of string theory could be curled up at a subatomic scale, invisible to us but still influencing the behavior of particles and forces. The geometry of these extra dimensions is thought to play a crucial role in determining the properties of particles and forces in our four-dimensional world. Different compactification schemes could lead to different sets of particles and forces, perhaps even explaining why our universe has the specific laws of physics that it does. In the mid-1990s, string theory underwent another revolution with the emergence of M-theory, a more encompassing framework that sought to unify the different versions of string theory that had emerged over the previous decades. M-theory introduced a new ingredient: membranes, or branes for short. These branes are higher dimensional objects that can exist within the full 11-dimensional spacetime of M-theory. While strings are one-dimensional objects like lines, branes can have 2, 3, or even more dimensions. Our universe, according to one interpretation of M-theory, might be a 3-dimensional brane floating in a higher dimensional space. Other branes, perhaps representing other universes with different laws of physics, could exist parallel to our own, interacting with us only through gravity or other subtle effects. This multiverse picture, while highly speculative, is a natural consequence of some M-theory models. It suggests that our universe might not be unique, but could be just one of countless universes, each with its own set of physical laws and constants. String theory and M-theory are undeniably elegant and mathematically compelling frameworks, but they remain highly speculative. The strings and extra dimensions they predict are far too small to be directly observed with our current technology. However, physicists are actively seeking indirect evidence that could support or refute these theories. One avenue of investigation is the search for supersymmetric particles at high-energy particle accelerators like the Large Hadron Collider. Supersymmetry is a theoretical concept that predicts partner particles for all known particles in the Standard Model. Another promising area of research is the study of the cosmic microwave background radiation, the faint afterglow of the Big Bang. Tiny fluctuations in this radiation could provide clues about the physics that governed the universe in its earliest moments, potentially revealing signatures of string theory or other quantum gravity effects. The search for experimental evidence is crucial to determining whether string theory and M-theory are more than just beautiful mathematics. It's a quest that pushes the boundaries of our technological capabilities and our understanding of the universe's deepest secrets. The answer to whether these theories truly hold the key to a unified theory of physics might lie just beyond the horizon of our current knowledge. The pursuit of a God equation, a single formula to encapsulate the universe's workings, holds an undeniable allure. It speaks to a deep-seated human desire for order. But even if we were to discover this elusive equation, what then? Would it truly mark the end of physics? History teaches us that scientific progress is often about refining our questions. The search for knowledge is an ongoing journey of exploration. The history of physics is littered with discarded theories, once dominant paradigms that crumbled in the face of new observations. Newton's laws of motion were ultimately superseded by Einstein's relativity. Even today, our best theories are known to be incomplete. This constant evolution of scientific understanding is a strength. Scientific truth is provisional, always open to revision. The universe is far stranger and more awe-inspiring than we can imagine. The quest for a unified theory is a testament to human curiosity, our drive to understand the universe. Whether or not we find a single equation, the journey has transformed our view of the cosmos. We've peered into atoms, unraveled stars' secrets, and glimpsed the Big Bang. The universe remains a source of endless wonder. As we stand on the precipice of the unknown, peering into the depths of the universe with ever more powerful instruments, we are struck by a profound realization. The cosmos is a symphony far grander than we imagined. Our quest to find the God equation, that elusive formula encapsulating the universe's workings, has been a journey of triumph and humility. We've scaled mountains of knowledge, from Newton to Einstein, from quantum mechanics to string theory. We've glimpsed the echoes of the Big Bang, unraveled the secrets of black holes, and pondered parallel universes. Yet for all our progress, we are still left with more questions than answers. The universe guards its secrets jealously, challenging us to push the boundaries of human ingenuity. The God equation remains elusive, a tantalizing prize that beckons us forward. But perhaps the true value lies in the journey itself. It's in the act of questioning, of exploring, that we truly connect with the universe's grandeur and mystery. The search for a unified theory of the universe is a testament to human curiosity. From the earliest stargazers to modern physicists probing atoms, we are driven by a desire to understand the world. This thirst for knowledge drives us to explore new frontiers. It's a legacy passed down through generations, from ancient philosophers to today's scientists. The quest for the God equation continues this legacy. The act of searching enriches our understanding of the universe. So, what's the answer? Is there a God equation? Does the universe hold a secret formula, a master key that unlocks all its mysteries? We don't know, and that's okay. The beauty of science lies not in possessing all the answers, but in embracing the unknown, in acknowledging that our understanding of the universe is always evolving. The search for a unified theory is far from over. New discoveries, new technologies, and new ways of thinking are constantly reshaping our understanding of the cosmos. What seems impossible today might become the breakthrough of tomorrow. The key is to remain open to possibility, to cultivate a sense of wonder, and to never stop asking questions. As we conclude our exploration of the God equation, let us remember that the universe is a vast and mysterious place, full of wonders yet to be discovered. It's a universe that invites us to explore, to question, and to never take our existence for granted. So keep looking up at the stars, keep asking the big questions, and never lose your sense of wonder. The universe is full of secrets, and who knows what amazing discoveries await us on the horizon. The journey of exploration has just begun.